Water Quality Solutions for Farmers and Landowners. This webinar is being recorded, and the recording will be shared to University of Illinois Extension's YouTube page. You will receive an email once it becomes available with the direct link. We ask that you please keep your camera and microphone off for the duration of the webinar. And please feel free to type your questions into the chat box at any point throughout the presentation. At the conclusion of the webinar, we will post a link to an evaluation, and we ask that you please fill it out. Your feedback is important to us and helps guide future webinar topics. Today's webinar is part of our Everyday Environment webinar series, and this webinar is a certified green event through the Institute for Sustainability, Energy, and Environment at University of Illinois. We recognize the importance of sustainability and encourage you to think about ways that you can be sustainable in your everyday life. We also want to extend our thanks to Becky Buckrop for setting up the registration for today's event. Today's speakers both work for Illinois Extension. Rachel Curry is a Watershed Outreach Associate who works in 2 nitrogen priority watersheds as listed in the Illinois Nutrient Loss Reduction Strategy. She is based out of the Galva office. Jennifer Jones is also a Watershed Outreach Associate who works in 2 phosphorus priority watersheds as listed in the Illinois Nutrient Loss Reduction Strategy. She is based out of the Effingham office. Now I'll turn it over to Rachel to get started.
All right, well, thank you, Erin. Today we are going to give you a brief background on watersheds as well as the Illinois Nutrient Loss Reduction Strategy before we're going to dive into some edge of field practices to help improve water quality and nutrient loss. Drainage water management, saturated buffers, bioreactors, and constructed wetlands are just some of the possible practices that can be used to reduce nutrient loss and improve water quality that are part of the Illinois Nutrient Loss Reduction Strategy. So a watershed is land that water drains across or under on its way to the nearest water body. All of the water in a region eventually drains to ponds, streams, lakes, or rivers. Even though watersheds come in different sizes, what happens in one region affects everything downstream of it. In Illinois, everything eventually drains to the Mississippi River. And so that means that the impact we have on water quality not only affects the local water bodies, but also the Mississippi River and the Gulf of Mexico. In addition to maximizing plant growth and nutrient use efficiency, a critical reason that we try to mitigate nutrient loss is the hypoxic zone in the Gulf of Mexico. The red zones outlined in black are regions with less than 2 milligrams per liter of oxygen, making them completely uninhabitable to marine life. Anything that can't leave the area will suffocate. The hypoxic zone is created by algal blooms, which are a result of excess phosphorus and nitrogen. Once the excess nutrients are used up or the seasons change, the algae will die off and their decomposition uses up an enormous amount of oxygen. NOAA recently released its most current report on the hypoxic zone on August 3rd, 2021. The 2021 Gulf of Mexico hypoxic zone was reported at approximately 6,300 square miles, which is equivalent to 4 million acres of habitat that is potentially unavailable to fish and bottom species. The hypoxic zone in 2021 was larger than average and almost 3 times larger than the 2035 target that's been set by the Hypoxia Task Force. This graph shows the size of the hypoxic zone each year since 1985. The goal level is the lower dashed line, and the 5-year average is the top dashed line. And the last bar is where we are now. Beyond this being an environmental issue, the hypoxic zone has serious economic implications for fishing and tourism industry in the Gulf states. The goal of the hypoxia zone is to be around an area of about 1,900 square miles. And while it's important to keep in mind that algal blooms impact our own local watersheds and can result in the closing of recreational areas in Illinois and decreased drinking water safety. So this brings us to the nutrient loss reduction strategy. The US EPA required that the 12 highest contributing states that drain into the Mississippi River create plans on how each state can reduce its nutrient loss. The Illinois plan was released on July 21st, 2015, and addresses nutrient loads from point sources, urban stormwater, and non-point sources. The interim goal is to reduce nitrate nitrogen loss by 15% and total phosphorus loss by 25% by the year 2025. The final goal is to reduce nitrate and phosphorus losses by 45%. Since the plan was released in 2015, we've had two biannual reports that have been published. The first was in 2017 and the second was in 2019. There is a third report coming out a little bit later this year. Now you have some background information. Let's move on to the edge of field practices. And we're going to start with drainage water management, which is also called controlled drainage. And though it's technically not considered an edge of field practice, we're going to include it in our talk today. So drainage water management, or controlled drainage, is the process of adjusting the elevation of a drainage system outlet called a control structure to control the volume of water leaving the field and reduce nutrient loss. The picture on the right compares conventional drainage to controlled drainage, and the controlled drainage structure can be used to adjust the height of the water table by adding or removing gates or stop logs. Control structures can be either manual or automatic. Stop logs or gates are inserted or removed to control the height of the water table, depending on the time of year. A typical management scenario involves raising the outlet level post-harvest to reduce drainage and nutrient loss during the non-growing season. Then the stop logs are removed prior to spring to lower the water table, which will help improve the trafficability and allow for field operations. Following spring operations, stop logs are put back into place to reduce nutrient loss and potentially store water from spring rains to be available later in the growing season. Drainage water management, or DWM, is an Illinois Conservation Practice Standard 554 and is the process of managing the drainage volume and water table elevation by regulating the flow from a surface or subsurface agricultural drainage system. The purpose of the DWM is to reduce nutrient, pathogen, and pesticide loading from drainage systems to improve productivity, health, and vigor of plants and reduce oxidation of soil organic matter. DWM is especially applicable in highly permeable and organic soils. Management decisions are based on the time, stage of the water held in ditches, pumping schedules, and coordination of these factors with rainfall, season, crop needs, and soil requirements. The picture on the right is of the installation of a control structure. And in the middle, you can see where the stop logs or gates can be added or removed as needed. Drainage water, sorry about that. DWM can be used with any new or existing tile drainage system, both surface and subsurface drainage. DWM is typically used on land where the average slope is less than 1%. And for land with steeper topography, DWM can be used, but will require additional control structures, which will increase the total cost. DWM should be used in areas where drainage is needed during certain periods of the growing season and where it might be advantageous to limit outflow at other times. For example, if you are in an area that has drought conditions that are intermittent and short, or in areas where a seasonally high water table is within 18 inches of the surface during the growing season, those would be possible locations for DWM. You also need to have at least 15 acres of contiguous surface area. The map denotes land that has a high probability of being suitable for a controlled drainage. And the map is designed to give a broad picture of locations in the region that are likely to be involved in controlled drainage activities, but controlled drainage is not limited to the areas indicated on the map. And as with everything, there are pros and cons to drainage water management. The pros include reducing nutrient export through the tile drains by reducing drainage volume, reducing surface runoff and erosion, allowing the adjustment of the water table and water storage, and potentially increasing or improving yields. However, currently the data is limited and inconclusive on that. Cons would include that it's used primarily on flatter topography. You're going to have increased installation, operation, and maintenance costs, as well as increased management to operate and maintain. And with that, I'm going to hand it over to Jennifer to discuss another edge of field practice.
Thank you, Rachel. I am going to request control from Rachel really quick.
There you go.
All right, awesome. Thanks everyone for being here with us this afternoon. So my name is Jennifer and I will be continuing on with the next practice. Today we'll be talking about saturated buffers as well. So as Rachel mentioned earlier, the next nutrient loss reduction strategy biennial report will be coming out soon, hopefully in the next couple months. And so actually what's exciting about this upcoming report is that saturated buffers will be added as one of the new best practices recommended in the nutrient loss reduction strategy. And so this came down through the science committee of the nutrient loss reduction strategy. They reviewed a lot of scientific research to show that saturated buffers are a good way to improve water quality in Illinois. And so it is being adopted into the nutrient loss reduction strategy. So that is pretty exciting. And I also want to thank Jill Costell with the Wetlands Initiative for providing much of the following information. Okay. Rachel, there. Okay. So what is a saturated buffer? Saturated buffers store water within the soil profile of field buffers by diverting tile water into shallow laterals that raise the water table within the buffer and slow outflow. Okay, so that sounds kind of confusing, but if you look at this image here on the right, you can see a conventional outlet is in the picture on the left. And so when we have tile drainage in fields, this is showing a situation where the tile is underground, going underneath the buffer and exiting into a stream or ditch. And so what a saturated buffer does instead on the right is we insert one of those control structures like Rachel just talked about, and a perforated pipe is installed to run parallel to the field or to the stream or ditch. And so then water goes, instead of immediately exiting into the stream or ditch, it is forced to go into that perforated distribution pipe. And so what happens then is that the water is pushed out into the saturated buffer and allowed to percolate through the soil. So Rachel, I might just need you to advance the slides for me. You can go to the next slide. Okay, thank you. So how exactly does a saturated buffer work? So while the water is working its way toward the stream underneath the ground, the soil and growing plants that are on the surface are naturally filtering out some of those nutrients that otherwise would have been directly deposited into the stream if we had allowed the tile water to just exit immediately into the stream. So additionally, when the buffer becomes fully saturated and anaerobic conditions are reached, which anaerobic means no oxygen, the denitrifying bacteria that are in the soil can work to convert nitrates to nitrogen gas. So nitrogen gas is a safe form of nitrogen. Our oxygen, or our air that we breathe every day, is 78% nitrogen gas. So we would rather have nitrates, instead of going into our water, we would rather convert them into a safer form like nitrogen gas. And so the bacteria use the soil as their carbon source or their energy to convert the nitrates into nitrogen gas. And additionally, if excessive amounts of precipitation were to fall at once, so if we were to get a big rainfall, there is a way for water to bypass the saturated buffer in order to prevent water backing up and flooding the field. So we don't want this practice to cause flooding in the field. If we get a lot of rain, we want it to work efficiently. So there is a way with that drainage control structure to allow the water to just go out into the stream immediately instead of being pushed through the buffer itself. Okay, next slide, Rachel. Okay, and saturated buffers are the Illinois conservation practice number 604. And so Rachel talked about the conservation practice standard for the drainage water control structures as well, but just a little background, a conservation practice standard is developed by the USDA Natural Resources Conservation Service, and it's science-based. So these standards help build practices that will perform and last as expected. And so each conservation practice standard includes the practice name, its unique code, a unit of measure for it, the definition and purpose of the practice, conditions that are necessary for the practice to be installed, criteria for the practice, plans and specifications, operation and maintenance, and scientific references. So for each practice, NRCS creates these standards so that they can be used by everyone to make sure the practices are being installed correctly and in a way that they will perform well for a long time. So on this slide, these are the main conditions and criteria necessary to install a saturated buffer. And so Erin just dropped the link into the chat for the conservation practice standard if you want to look through that too. There's a lot more information than just this, but these are some of the highlights for conditions that are necessary. So we do need a restrictive layer or a water table in order to create those saturated conditions in the buffer so that whenever water is diverted into the buffer, it doesn't just drain through. Like if we had a sandy soil, it might just drain through too quickly. We want to create anaerobic conditions there. And we need the absence of pockets or layers of high conductivity soil that could provide preferential flow paths. So again, we don't want the water to find a way where it can just quickly flow through the soil profile. And this is a really big one. So to install a saturated buffer, you need a minimum of 1.2% organic matter in the top 2.5 feet of the soil. So we need that carbon source for the bacteria in the soil to be able to convert the nitrates into nitrogen gas. So they need carbon from the organic matter. So we have that minimum amount necessary in order to install this practice. We need the absence of abandoned drain pipes or clay tile that's maybe been in the buffer from previous years. We need a minimum of a 30-foot wide vegetated buffer zone. So that's the area that the saturated buffer, the tile, perforated tile will be installed into, which you can kind of see that in the picture on the right. You can see the perforated pipe has been dug and buried down the center of that buffer. So we need one that's at least 30 feet wide. And then of course we need the water control structure similar to what Rachel was just describing. So you can see that in the forefront of the picture here, where the water will go through there in order to reach the perforated pipes. All right, next slide, Rachel. Okay, so where should a saturated buffer be used? A little bit of this is repetitive from what we just talked about, but again, of course, we need a drainage system. So we need a field that has a tile drainage system installed, and it needs 6 to 12-inch mains. There needs to be at least the 30-foot width of a perennial vegetative buffer. We need stable stream banks. So if the tile's dropping out into a stream, it needs to have stable banks. Again, we need the buffer to have at least 1.2% soil organic matter in the top 2.5 feet. We need no sand or gravel layers along the length of the distribution line, that perforated pipe, because again, we don't want the water to just drain out of the soil immediately. We need it to become saturated. And we need, again, that restrictive layer to create that saturated zone within soil. And then it works best when the tile outlet is lower than the contributing field. So we don't want the tile outlet to be higher than the field that the tile is draining out of. And so this picture on the right is a saturated buffer installation that was in Champaign County a couple of years ago. And so you can see they were just putting in the perforated tile here down the center of the buffer. And let's see, I do have one last slide. There we go, saturated buffers. So the pros and cons. Pros of this are that it decreases the nitrate nitrogen. Of course, that's the main draw. It's decreasing those loads going into the ditch or stream. It decreases turbidity or the cloudiness of the water and the volume of water in that waterway, because it keeps more in the field or in that buffer. It requires little annual maintenance. Once it's installed, you just need to maintain the level of the stop logs in that drainage control structure. And that's pretty easy to do. It does stabilize the stream banks itself, because it's decreasing the amount of water that's exiting into the stream, and it's decreasing the rate that it's exiting into the stream. So it reduces the amount of erosion that the stream bank might be seeing. Having that 30-foot wide buffer does provide wildlife habitat. And again, it reduces the peak stream flow, kind of what I was just talking about, where if we get a big rainfall, all that water is not exiting into the stream as quickly. So some negatives of saturated buffers are that high flow events or extremely wet years can bypass the system. So, if we get a 5-inch rain, it's possible that some of that will have to go through the bypass instead of going into the saturated buffer, which is okay. We don't want the field to be flooded, so we have to have that bypass feature. But it is possible that we could not capture all that nitrogen that's exiting the field in that case. It does require a length of the vegetated buffer required along that ditch or stream. So that could be challenging for some people if the buffer is not already in place to have to get one established there. It does require soil with that higher organic matter, so that 1.2% minimum, and we need low levels of sand or gravel. So that does kind of limit the sites where the saturated buffer can be installed. And it must have stable banks. So there's some pros and cons there. I also want to share with you a new fact sheet on saturated buffers produced by Dr. Laura Christensen out of U of I, and Aaron just shared that into the chat box as well. So that's another great resource if you're more of a learner by reading and you want to read through that fact sheet. It's a great resource. So I will turn it back to Rachel for the next part.
Great, thank you. So next we are going to discuss the Woodchip bioreactors, and the picture on the slide is of an almost completed Woodchip bioreactor, and this was provided by the Soil and Water Conservation Society's Conservation Media Library. So Woodchip bioreactor is a lined trench filled with a carbon source. Oftentimes that's going to be wood. Wood chips are the carbon source of choice for most bioreactors due to the longer lifespan of wood chips as compared to other carbon sources like corn cobs, corn stalks, or wheat straw, for example. The microbes are going to eat up the corn cobs a lot faster than they're going to the wood chips. So the drainage water is routed into the bioreactor by a control structure during a typical flow event, but it also allows water to bypass the bioreactor during times of high flow events, like Jennifer was just talking about. And then there's another control structure that's located at the other end, which is used to maintain the water level within the Woodchip bioreactor. So within the bioreactor, bacteria denitrifiers to be exact, convert nitrate into nitrogen gas through a process called denitrification, which Jennifer told you about. The bacteria use the wood chips as their food source and use nitrate as part of their respiration process. Bacteria can also breathe oxygen, which is why it's really important to have an anaerobic condition or the absence of oxygen. So then they'll force the bacteria to use the nitrates rather than oxygen. Bioreactors typically have two control structures, as I mentioned a few moments ago. The inlet diverts the water into the bioreactor, but allows water to bypass during a time of high volume. And a second structure is at the outlet of the bioreactor and can be raised or lowered to maintain the water depth within the bioreactor. Bioreactors enhance the natural denitrification process. So this illustration on the right is of a typical Woodchip bioreactor, and you can see the inlet control structure on the left, which also has the drainage location for excess water during high flow events. And then the control structure on the right is at the outlet. The Woodchip Bioreactor is Illinois Conservation Practice Standard 605, and it is defined as a structure that uses wood chips to reduce the concentration of nitrate nitrogen in subsurface agricultural drainage flow via enhanced denitrification, which is just a fancy way of what I explained just a few moments ago. And the purpose of the bioreactor is to improve water quality by reducing nitrate nitrogen in drainage water that is entering the watershed. So the design must be either to treat the peak flow from a 10-year, 24-hour drain flow event, treat at least 15% of peak flow with a hydraulic retention time of at least 3 hours, or to treat at least 60% of the long-term average flow from the drainage area. And the size of the bioreactor varies depending on the drainage area. It is typically a 4:1 length to width ratio or greater. And commonly bioreactors are about 100 to 125 feet long and about 10 to 25 feet wide. And that's all dependent on the available space as well as the drainage area. Wood chips are used in bioreactors, and so they should be reasonably free of soil and other contaminants. The choice of wood chips used should also include no high tannin woods like cedar or redwood, and the wood should not have been treated, and wood chips typically are about 1/4 to 1 inch in size. And Erin is sharing the conservation practice standard in the chat if you would like to read through some more. So bioreactors are ideal for drainage areas of 30 to 100 acres, and they can be added to existing tile drainage systems as long as you have 6 to 10 inch mains with constant flow, and it's primarily subsurface drainage. Bioreactors should be placed in areas of the field where equipment can operate without driving over the bioreactor chamber, like buffer strips or grass area, so that no land is taken out of production. And the bioreactor should be placed in an area where the elevation of the bioreactor allows for proper drainage of the crop fields. Again, like Jennifer mentioned, for saturated buffers to make sure that there isn't any ponding in the field. And again, there are pluses and minuses to woodchip bioreactors. The positives include reduced nitrate leaving the field through drainage and surface runoff. It doesn't impact in-field management. The wood chips last typically 10 to 20 years before they're going to need to be replaced. It requires minimal effort, just normally adjusting the stop logs at the outlet, control structures, twice a year, depending on the year. And it is overall fairly low maintenance once it's installed. the area above the bioreactor may potentially provide habitat benefits depending on the vegetation that is chosen. Some of the negatives include the high upfront cost, which can range from $7,000 to $10,000. And in times of high flow events, the water is going to bypass the system, which means that it's not taking the nitrates out. There can be a lack of available and affordable wood chips. The startup outflow will contain organics. There's incomplete denitrification can occur, and that will result in nitrous oxide, which is a greenhouse gas. There's the high retention time, which can increase hydrogen sulfide gas and methyl mercury. And the process in the bioreactor is a biological process. So nitrate removal can be negatively impacted by cooler temperatures or too high of flow rates. And in the chat, there's a link to the Woodchip Bioreactor fact sheet that's produced by Dr. Laura Christensen's lab. And now I'm going to hand it off to Jennifer to continue our discussion of the edge of field practices.
Okay, thanks, Rachel. All right, so the final practice that we will discuss today is constructed wetlands. And I want to say thanks again to Jill Costell for providing a lot of this information. And I encourage you to check out the Wetland Initiative's website for additional information on constructed wetlands, which Erin just shared that link in the chat as well. All right, next slide. Okay, so what is a constructed wetland? So constructed wetlands are artificial ecosystems. So note that artificial. They are designed and built specifically to treat water. So that could be wastewater, stormwater runoff, or tile drainage in a farm field. They are engineered systems. So again, the purpose of a constructed wetland is to treat wastewater or to improve water quality of stormwater runoff or tile drainage flows. So this is not to be confused with like a wetland restoration or wetland creation or wetland enhancement, where the purpose of those is to restore, create, or enhance wetland functions other than wastewater treatment or water quality improvement. So with a constructed wetland, the main reason we're doing this is to improve water quality. So next slide. Okay, so how does it work? So with a constructed wetland, tile water containing the nitrate load is discharged into the wetland. So on the left side of this image, you can see that black arrow that says inflow. So that's the tile water flowing in. There is a microbial community that's attached to the sediments and plants. So the sediment down there at the bottom of the image and the plant roots, of course, we have microbes there that breathe in the nitrate because there's no oxygen there for them to breathe in whenever we have a saturated wetland. And so the oxygen gradients allow for both aerobic and anaerobic conditions to occur near that interface, the sediment water interface, and then biofilms on plants. So then carbon, again, carbon is the energy source for the bacteria. That carbon supply comes from the plant roots, exudates, and the accumulated decomposing plants, algae, fungi, organisms, etc. All that stuff at the bottom of the wetland that's dead, that's where the bacteria are getting their energy from to do this denitrification process. And so carbon can be the limiting factor for denitrification. So if we don't have enough of that dead stuff there at the bottom, that could limit the amount of denitrification that can occur. Plant growth cycles seasonally store and release nitrogen and phosphorus. So in the image, you can kind of see the plants, of course, are taking up nutrients still to grow. So they're taking up some of that phosphorus and nitrogen. And as their cycles go through the season, they decompose and it can release nitrogen and phosphorus back into the wetland. Okay, next slide. Okay, so constructed wetlands are the Illinois Conservation Practice Standard number 656. And so their official definition is an artificial ecosystem with hydrophytic vegetation for water treatment. And so hydrophytic vegetation, of course, means plants that can grow in water. And so Erin just dropped in that conservation practice standard into the chat as well. And so here are the main conditions and criteria that are necessary to install a constructed wetland. We do need to build a shallow pond with an auxiliary spillway. We need to use a water control structure to maintain a normal operating pool and to manage for the plant community establishment. So again, the plants that go into a wetland are hydrophytic, so they need water present. We don't want the wetland to dry up, or else we might not be able to establish our plants. We need to account for accretion and wetland volume. We need to maximize the hydraulic retention time and flow path. So again, we want to retain water in the wetland as long as we can, because that allows for more denitrification to occur. And so that's the whole point of the wetland, is to allow that denitrification process to occur. So we don't want the water to just flow through it super quickly and exit. We want it to be retained. And then there is specific guidance for cropland drainage water treatments on the CPS. And so some of that is to daylight the tile into the wetland such that the invert is above permanent pool elevation. We need at least 50% of the area should be 12 inches or less at permanent pool elevation. The wetland treatment area must be at least 1% of the contributing drainage area. So every wetland is going to be different depending on your drainage area. Wetlands will be different sizes just depending on how much you're trying to treat, how much water you're trying to treat. And the wetland treatment area is between 24 inches below and 12 inches above the permanent pool elevation. Okay, so next slide, please. Okay, so where should it be used? Again, this is just some guidance. We need sufficient tile drainage. So of course, kind of the same with all the practices we've been talking about, we need to have tile drainage to be able to implement them. And so we are diverting that tile flow into the wetland. We need an area for the wetland and surrounding buffer. And so preferably that would be on low or non-profitable land. We don't want to take out your highly productive land. If we can avoid it, we want to just use something that maybe isn't producing as highly or is already in a buffer perhaps. We also want it to be in a lower spot in the field so that we can daylight the tile, which daylight means that's where the tile is coming out of the ground. So daylight it and not impact your crops nearby. Again, we don't want it flooding the fields. We want it to go into the wetland. We need for the site to have soils that are capable of holding a water table. So they either have a shallow water table or they have sufficient clay at the depth to serve kind of as a liner for the wetland. So again, it's kind of the same process as a saturated buffer. We don't want like the water to just drain out. Obviously, we want it to be held within the wetland. And so we need that shallow water table or clay to help us retain the water there. We need soils that can grow plants, of course, so loamy or medium texture topsoil. And we need, well, so this isn't necessary, but it is ideal to have prior converted farmland, so land that was formerly a wetland area. It's nice to be able to just take that land and convert it back into a constructed wetland, but that's not required. And then we do need bank stability if that's applicable for your particular site. Okay, next slide. All right, in constructed wetlands, pros and cons. So the pros are it especially removes nitrate, and current research is showing that it can also remove some phosphorus as well. They are a proven technology in agriculture, but also in municipalities and industrial applications. Constructed wetlands are very effective and efficient at what they do. They can receive surface intake water and surface runoff water as well. And they require very little annual maintenance once they get established. They do have a very long life as well, so 30 plus years. They do not require cropping system changes. So this is just a practice, like the title of this webinar is Edge of Field. So these wetlands are on the edge of the field. You don't have to change what you're doing in field necessarily. It provides benefits besides just water quality. So we can also create wildlife habitat. So if you're into birding or bird hunting, you can attract some cool species of birds as well, but it can be recreation and limited flood storage as well. And you can qualify for some USDA Farm Bill programs to help implement a constructed wetland. And so some of the negatives are that they can be expensive. Like I said earlier, every wetland is different because it just depends on how much drainage area you're trying to treat. So it's a case by case, but they can be thousands of dollars, and they typically require excavation. So that's where a lot of the cost comes from, is you're having to move soil. And there is that, because of that, that's a high upfront cost. And it does take more than a day to implement. And you could potentially be taking land out of production just because of the size of the wetland. But again, it just depends on how much area you're trying to treat. And it can take up to 1 to 2 years to be fully operational, because it takes a while for those wetland plants to become completely established. And it is possible it could attract some nuisance species. Okay, and I just want to say there are some cost share dollars available with constructed wetlands, like I mentioned, through NRCS or USDA farm bills. So that is one thing that can help with some of those costs. All right, so if you are interested in learning more, we do have a few resources here. So the first is the Illinois Nutrient Loss Reduction Podcast. This is a podcast that Rachel and I actually co-produced with Todd Gleason, who is a communications specialist for Extension. And Aaron just dropped the link into the chat. So we have currently 39 episodes. Each episode focuses on a different conservation practice that could be adopted to reduce nutrient loss. And so each episode features different experts depending on the topic. It also features farmers who have successfully implemented this practice. And you get to hear kind of some of the challenges they went through, but also how they work through those challenges to make that practice a success on their farm. So I highly encourage you to check out our podcast if you're interested in learning more. I also want to point out the Illinois Sustainable Ag Partnership. So this image here on the bottom is showing all of the partner organizations that are included in ISAP. And so Extension is one of the partners, but you can see we have a really good representation of groups in Illinois who have come together in order to help reduce nutrient loss leaving Illinois. And so this group puts together a lot of excellent resources, and Aaron did share the website in the chat, so I encourage you to go there as well. ISAP actually just recently did a great series on the carbon market situation in agriculture, so if you're wanting to learn more about that, it's recorded and on the ISAP website, and I highly encourage you to check that out. It was a great series. And finally, another resource, there's so many resources out there, but another good one is the Soil and Water Conservation Society's Conservation Media Library. And so we pulled a lot of our pictures from there, but they also have presentations on these different practices and fact sheets and just different things if you're wanting to just learn a bit more. All right, next slide. We want to thank you so much for being with us today and invite you to join our colleague Dwayne Friend on September 9th for the next webinar in the Everyday Environment series. So Dwayne will discuss soil, climate, and carbon. And the registration link was just put into the chat by Aaron. All right, next slide. So again, thank you on behalf of Rachel and myself. We're so glad you could join us today. We do ask that you complete the evaluation for this webinar. It really helps us to just know how we did and what kind of information you might want to learn about in future webinars. So you can scan that QR code if you have a smartphone, or you can just click the link that Aaron dropped into the chat. We also have the link on the slide here. If you want to just write it down, you can do that as well. And Aaron just put Rachel and I's contact information as well into the chat. So if you want to email Rachel or I for more specific information, we are more than happy to send you resources and talk with you about ideas or practices you might want to implement on your land. So thank you, and I'll turn it over to Aaron to lead us through some Q&A.
Great, thank you so much, Jennifer and Rachel. It was a very informative webinar. We have had a couple of questions. The first question early on in the presentation, someone was saying that they had friends in Florida who talk about the red tide. Is that related to hypoxia that you mentioned?
Okay, yeah, I think that was the part when Rachel was talking probably about hypoxia. So from my understanding, yeah, the red tide actually is a form of algae. And a lot of times I think the red tide is seen a lot more like near the shore, just because when people are out walking, they can see it, and you definitely don't want to get in algae. I don't think that was one thing we really hit on, but even here in Illinois, if you have algae growing on your ponds, do not swim in that water. Don't let your pets or like kids drink from the water or anything, because it can be toxic. So that's something to avoid. But yes, the red tide is a form of algae as well.
Okay, great. Staying on the same topic regarding the hypoxic zone, do we know why the levels have jumped so much in the last 5 years?
Rachel, do you want to take a shot at that one?
Not really, but so each year they sample at approximately the same time, and as like last year the levels went down, but that's because the survey was done right after Hurricane Hannah, and so that caused some issues with the data, sorry, I'm complete brain fart right now.
No, yeah, that's a good point to mention too. On that one graph that we showed, last year's was really low, like Rachel mentioned, because Hurricane Hannah disturbed the water column. I guess I don't really know either, like all the specific issues that go into it, but nutrient loss is definitely one of the biggest reasons that we are seeing the hypoxic zone growing every year. Just Illinois is not the only one contributing to the issue. Of course, there are many states that drain into the Gulf of Mexico, and we're all contributing nutrients, but also sediment. And so that is, in my opinion, the biggest reason that the hypoxic zone is getting bigger. And that's why we're trying to slow that growth.
Okay, great. We had a question when you were talking about saturated buffers. Again, just to clarify why the soil needs that organic material. I think you mentioned the 1.2% minimum. If you could talk a little bit more about why that's needed.
Sure. Yeah, so we need that minimum 1.2% organic matter because it's the carbon source for the bacteria in the soil. So again, the way the saturated buffer works is the soil becomes saturated and it causes anaerobic conditions to occur, which anaerobic means low to no oxygen. And so the bacteria are then they're eating the carbon, and that's their fuel to convert the nitrates into nitrogen gas. And so we need that organic matter there because organic matter is carbon. And so we have to have that minimum amount there for the bacteria to be able to chow down on and convert that nitrate into nitrate gas.
Okay, great. Our next question, I'm not sure I completely understand, but someone was asking how the tiles take out the nitrites. And I think if you could just clarify about how adding in the extra drainage tile helps facilitate that process.
Okay, like in the saturated buffer, maybe?
I think it was after the bioreactor. Sorry, forgot to mention. That's when the question came in. I'm not sure if that's what it was referring to.
Okay.
Well, I can take a stab at it. So nitrates are incredibly mobile in the soil. And so as the water is moving through the soil, it's taking the nitrates with it. And so when the water and the nitrates get to the tile drainage, when the water goes, the nitrates go too. And so with all of these practices, we're trying to slow down that drainage water with the nitrates from getting off of your field and losing them, which also causes other issues downstream. But it's also taking the nitrogen away from your plants. And so these are just some ways to help keep the nitrogen in the soil and convert it from a form that is good for plants, but not, and for algae, but maybe not so much the results of the algae. I don't know, does that kind of answer your question?
I think so. Yeah, that was great. Okay, that is all of the questions that I see so far in the chat box. So I'm going to say we'll wrap it up for today. Thank you so much, everyone, for joining us, joining Rachel and Jennifer. And if you have extra questions that you think of, again, their email addresses are in the chat box. You can feel free to reach out to them directly. But again, thank you. Enjoy the rest of your day. And we hope to see you next month for our next Everyday Environment webinar. Take care, everyone.